Okay, sorry for the delay. There were experiencing some technical difficulties. So welcome everyone to the afternoon session. Our first speaker is Ekaterina Fokina, and she will be talking about bi-embeddability relation of computable structures.
Thank you so much. A couple of weeks ago, I was asked about bi-embeddability, given another talk, and so I decided to give an overview of various areas where bi-embeddability appears in the context of computable structure theory. So it will be a summary of several directions and quite some open questions. So if someone gets interested in those open questions, I'll be very happy. And well, in particular, I will show how those results relate to analogous results about more classical directions, about isomorphisms and its effective versions, computable isomorphism, and things like this. And some results are easier for bi-embeddability, some results are more complicated for bi-embeddability, some results transfer trivially, some results are not at all trivial and not clear. So it is quite a nice picture. Okay, so there will be 4 motivating questions, so 4 directions in the song.
Excuse me, some people are complaining about the quality of the sound. Can we please use this?
Yep.
So, thank you very much. It's on.
Okay. So, can you hear me here? Okay. So there will be 4 motivating questions and 4 directions that I will try to explain, hopefully. So the first kind of results are about the question, how hard it is at all to determine that 2 computable structures are bi-embeddable. Okay, and so here I write everywhere. Okay, no pointer, but here I write everywhere equivalent, but mostly I will talk about bi-embeddability, sometimes also isomorphism and some other equivalence relations, right? So to give you the big picture, but yeah. So for the moment, let's think about bi-embeddability. So how hard it is to determine that 2 computable structures are bi-embeddable. That would be the direction that motivates the first kind of results. And the first open questions in the, from this talk. The second question is about existence of a computable bi-embeddable copy of a structure. So we have an arbitrary countable structure, and we want to know if we have a computable copy, but not up to isomorphism, but something similar, well, something similar to our structure and computable, yeah, in this sense, a bi-embeddable computable copy. The third type of questions is about computable categoricity, also up to bi-embeddability. Yeah? So we have 2 computable bi-embeddable structures, and we want to measure the complexity of those embeddings between 2 structures. And the fourth question, this is, well, less classic, let's say, but the question that I've been working on in the recent years, and I think it's quite interesting. And we also have some results about bi-embeddability here. So suppose we have a class of countable structures, and we are observing finite pieces of one of the structures. And the task is to say which of the structure we are observing, maybe not exactly, but up to bi-embeddability. Okay, so these are the four motivating questions, and this is how we are going to proceed. So just going through them one by one. Okay, so the first question about the complexity of being able to determine if two structures are bi-embeddable or somehow else equivalent. So this is the question about classification. So this is the setting. Suppose we have a class of countable structures, nice class. I will explain it in a moment what I mean by nice in this situation. And then, well, we assume that it is closed under isomorphism. And then we just pick all the computable structures from this class, identify them with the natural numbers through the indices of the atomic diagrams of those structures. So we get the index set for this class, the set of indices of all the computable members of this class. And well, by nice, I here mean that this index set is not too complicated. Well, in our case, mostly we will think about hyperarithmetical index sets. Okay, and then any relation on such a class, for example, bi-embeddability or isomorphism, or it doesn't even have to be an equivalence relation, some kind of binary relation, can be identified with a set of indices, with a relation on indices. So we have a relation E, and we identified with the relation on the corresponding indices of structures from this class K. Okay, so now it's a binary relation just on the natural numbers, and we can measure the complexity of those relations as the measure as relations on the natural numbers. So we use here a slight modification of the usual notion of computable reducibility. Computable reducibility on the natural numbers. In general, we have two equivalence relations on the natural numbers, and we say that one is reducible to the other if we have a computable function that behaves like this. So I and j are E equivalent if and only if the images are F equivalent. So here we have a slight modifications because we do not care about all the natural numbers, but we only care about this reducibility on those index sets or some hyperarithmetical subsets of the natural numbers. So here, instead of total computable function, we have a partial computable function that is defined on X and whose range is inside of Y. So it's a slight modification that to make it fit with these hyperarithmetical index sets. Okay, so and this is what we look at here, and actually the result about bi-embeddability was the first result in the series of results in this direction. We proved it with Cy Friedman when I just arrived to Vienna. And well, if you look at this definition here, that you see that if you have a class of structures with a hyperarithmetical index set, then the relation can be at most sigma 1,1, because we are talking about existence of a computable function. So, and we show that the bi-embeddability relation is actually as complicated as it possibly can be. It's sigma 1,1 complete. Okay, and here is the first open question. So we know that it is for graphs, let's say, as complicated as it's possibly as it can be. So the question is it as rich in a sense as it can be? So more formally, the question is the following. So suppose we have an arbitrary sigma 1,1 equivalence relation on omega, Is there a class of structures, K, with a hyperarithmetical index set, a class that is closed under isomorphism, that is such that the bi-embeddability relation on this class is exactly equivalent to this relation E. Okay, so we do not want this bi-embeddability. So we know that it lies on top, but we want to know if it's everywhere inside those sigma 1,1 equivalence relations. If we talk about Borel reducibility, yeah, so the same, well, similar setting, analogous setting, but for countable structures and Borel reducibility, then Cy-Friedman and Luka-Motoros proved this result in that case. Yeah, so theoretically, we could transfer these to computable structures, but with hyperarithmetical reducibility. Okay, but the question here, can we have it computable? Okay, so this is an open question. Okay, the same we could ask also for other equivalence relations, by the way. Yeah, so we proved that later we proved that the isomorphism is also sigma 1,1 complete, and we looked also at some, for example, on computable. Computable isomorphism, so it's also sigma 0,3 complete. So and for hyperarithmetical isomorphism, it's bi-1,1 complete. So there is quite some results of this kind. So for any of them, I would be interested in this kind of results. So can we find a nice class of structures such that the corresponding relation, whatever we choose, bi-embeddability, hyperarithmetical isomorphism, whatever, has exactly this complexity. Okay. Exactly this complexity as some chosen equivalence relation of, well, whatever possible complexity, whatever reasonable complexity. Okay, so I guess for isomorphisms will be very hard to do, but for bi-embeddability, I have hopes that it can be done. Okay, good. So let's move to the second question. Now the second question is about existence of a computable bi-embeddable copy of a structure. This is formalized using this notion of the degree spectra. Yeah, so this is a, let me start with this general definition. So suppose we have a countable structure and an equivalence relation. Then the degree spectrum of this structure with respect to this equivalence relation is just the set of degrees of all the E equivalent copies of A. And so if we talk about yeah, so by the way, this is the definition from our paper with Semukin and Turetsky, but there were also other papers with similar definitions, for example, by Antonio Montalbano, Julian. Well, other people also defined similar objects. Yeah, so the classical situation, if we consider the relation of isomorphism, this is the degree spectrum of a structure. Okay, so here just I list some of the known examples. Yeah, okay, cones. All the non-computable degrees, all the non-hyperarithmetical degrees are degree spectra of structures, like degree spectra with respect to isomorphism. But no countable union of upper cones can be realized as such a degree spectrum. Yeah. When we consider elementary equivalence instead of isomorphism, then we basically get the notion of the degree spectrum of the theory of a structure. Yeah, so if we start with a structure, so this will be degree spectrum of the theory of a structure as defined by Uri Anderson and John Miller. And well, here I also list some examples that show that there are degree spectra of structures that are not degree spectra of theories, and vice versa, degree spectra of theories that are not degree spectra of structures. Okay, so and we are interested, well, in the same for bi-embeddability, but before I move to bi-embeddability, let me for completeness say also, okay. So I want to say for completeness some other results, but it's not changing the slides. Okay, so anyways, I guess while I'm waiting, so what we did, we also studied degree spectra with respect to sigma n equivalence. So we say that two structures are sigma n equivalent to each other if their sigma, like finitary sigma n theories coincide. Okay, so this is some kind of approximation to this degree spectra of theories. And then we also showed that many of those positive examples about theories can be actually transferred to this sigma n spectra, starting with n greater than or equal to 2. Okay, and well, but not to 1. Yeah, sigma 1 theories are too weak to be able to well, to code something interesting to them. Yeah, but starting from 2, many results transfer from theories to sigma n spectra. On the other hand, we have examples of theory spectra that are not sigma n spectra for any n. And we also know that this hierarchy is in a sense strict. So we know that there exist sigma n plus 1 spectra that are not sigma n spectra, okay, for any n. Okay, an open question here is also interestingly enough, so we still do not know if every sigma n spectrum is actually sigma n plus 1 spectrum. Okay, or if every sigma n spectrum is also a theory spectrum. So this is something that we still do not know. Yeah, so I would be interested in that. Okay, so this is about this sigma n equivalence relations, and now let's go to yeah. Okay, to bi-embeddability. Okay, the bi-embeddability spectrum is defined in the same way. So we take the degrees of all the bi-embeddable copies of our structure. Well, quite obviously, the bi-embeddability spectrum is just the union of the isomorphism spectra, like usual degree spectra of the structures that are bi-embeddable with our structure. So the general question here is how are they related to each other, bi-embeddability spectra and the isomorphism spectra. And this is the case where bi-embeddability spectra are quite, well, bi-embeddability is quite hard to work with. So we do not really have that many interesting results here. Well, okay, so first of all, let me mention these results on this page. For some classes of structures like linear orders, abelian P groups, for equivalent structures, like every hyperarithmetical structure has a bi-embeddable copy. Okay, so the first two are real results with real proofs. The third line is just an obvious observation. Okay, but this obvious observation actually motivated us to look at other classes. Yeah, so for equivalent structures, we always have 0 in the bi-embeddability spectrum. What if we put a bit more structure on those equivalent structures? So we decided to look at strongly locally finite graphs. So basically, we get rid of all the infinite equivalence classes, and we put some internal structure on the finite equivalence classes. Okay, and we look what's happening there. Okay, so I'll talk about it in a minute. So, and first, let me tell you what we know in general about the bi-embeddability spectrum. Well, first of all, okay, we know that it is, as usually, either a singleton or upward closed. We know that cones are bi-embeddability spectra, everything but computable, everything but hyperimmune, those are bi-embeddability spectra. These results directly transfer from the classical isomorphism degree spectra case. And the reason it's what we call the BE triviality, like bi-embeddable triviality, in the following sense, that if we look at those examples for these above mentioned examples, then actually all bi-embeddable structures in those examples are actually isomorphic. So we do not really get more than isomorphism spectra when we look at bi-embeddability spectra of the same structure. So these results just transfer directly. So we still do not know if the union of two cones can be realized as bi-embeddability spectrum. And at the moment, I even have no preference to yes or no answer. So, okay. Good. So now about those strongly locally finite graphs. Okay, let's say that a strongly locally finite graph is open-ended if its finite component can be embedded into a larger component inside of the same graph. So these are the graphs that we looked at the first, together with Dino Rosega and Lucas Amaura. And for those, we could completely characterize how the isomorphism spectra look, the isomorphism types and their bi-embeddability types, how they look like. It's very well analogous to the case of equivalence structures. So it's in terms of character and some modifications of limit-wise monotonic functions, things like this. So here, for example, you can see for bi-embeddability, if we have an open-ended graph, then some Y computes a bi-embeddable copy. Excuse me. If and only if some specific set associated with this graph G is CE in this Y, where this trace G is just a set of indices of all finite graphs that are embeddable into our graph. Okay, and then for open-ended graphs, we at least have some non-trivial example of degree spectra, so something that is not a cone of the degrees, but on the other hand, we know that those open-ended graphs are really not good enough to get some rich variety of examples, because we know that the jump degree spectra, jumps of the degrees that are in this bi-embeddability degree spectrum, it will always be a cone for such open-ended strongly locally finite graphs. Okay, so we need to look further, and this is also something that we know for these open-ended graphs, that they all have this bi-embeddability basis. So it's another indication that they are not not really enough to get interesting example. The bi-embeddability basis, we say that the structure has a bi-embeddability basis if its bi-embeddability spectrum actually collapses to the isomorphism spectrum of one of bi-embeddable copies of the structure. So this is the bi-embeddability basis. So it might be the case that it is not, the structure is not bi-trivial, in the sense that it's not necessarily that all the bi-embeddable copies are isomorphic. So it might be that it has different kinds of bi-embeddable copies, but one of them, looking at its isomorphism spectrum, we already get everything. And this is what happens for these open-ended graphs. So one needs to look at some broader kinds of graphs here without this restriction, but at least we know that there exists some strongly locally finite graph with no B basis yet, so it's not open-ended anymore. So, but this is basically pretty much everything that we know about bi-embeddability in this context. So as I said, it's kind of quite tricky to do something with it. And the main question here, can we distinguish between isomorphism spectra and bi-embeddability spectra? So is there an isomorphism spectrum that is not a bi-embeddability spectrum and vice versa. Yeah, maybe restricted to some particular classes. Okay, some particular natural classes of structures. Okay, so for completeness, I also mentioned this result about elementary bi-embeddability proved by Dino Rosteger. So he looked at the relation of elementary bi-embeddability, and he transferred several known counterexamples from the case of isomorphism to the case of elementary bi-embeddability. And he also proved this result that for a graph G, there exists another graph G hat such that the elementary bi-embeddability spectrum of this new graph G hat consists of all the degrees that jump to the degrees in the bi-embeddability spectrum of G. Okay, so these are the open questions about this line of research. And now let's start with the third question about computable categoricity for bi-embeddability. So we now have two, let's say, computable structures that are bi-embeddable. So what is the complexity about, what is the complexity of the embeddings? So again, let's think about equivalence structures. So they will appear a lot throughout this talk. So suppose we have an equivalence structure with infinitely many equivalence classes of size 1 and infinitely many classes of size 2. So it is not computably categorical, but it is zero jump computably categorical in the classical sense, up to isomorphism. On the other hand, if we consider any equivalence structure which has infinitely many classes of size 2, and we do not care how many classes of size 1, it will be bi-embeddable with this structure A as above. And actually, those embeddings will be computable. We just send all the classes into a classes of size 2 always. So we wait for the next class of size 2 to appear. And that's where we send our elements. Okay, so bi-embeddable computable categoricity is different in general from the usual computable categoricity up to isomorphism. Okay, and actually, in some senses, in some cases, this is the case where it was easier to deal with it. Okay, so I will show you now some examples where it was easier to deal with it as with classical computable categoricity. So this is the definition, the usual definition of computable categoricity with isomorphisms substituted by embeddings. So we say that a computable structure is computably bi-embeddably categorical or computably BE categorical if its computable bi-embeddable copy is actually computably bi-embeddable. So we have computable embeddings in both directions. And this is something that we defined with Bajenov, Rosegrens, and Maurer. And you can also define all this up to an oracle and relative versions of this definition. And here is the first open question: do we have a syntactic description of relative BE categoricity? So that would be nice to know. Okay, for the isomorphism, we know we have such a thing, so it would be nice to know if we have something like this for bi-embeddable categoricity. So together with Bajenov, Rosegrens, and Maurer, we looked at BE categoricity for equivalent structures, and we compared it to the classical computable categoricity. And this is how the picture looks like. So we looked at computable categoricity, like computable isomorphisms and embeddings, then up to then relative to zero jump and relative to zero double jump. So we know that for equivalent structures, they are computably categorical and well, relatively computably categorical and relatively BE categorical with respect to zero double jump. So in that situation, we have, it's actually everything is equivalent. But for the computable case and for zero jump case, the situation is actually quite interesting. So we know that computable categoricity is not the same as computable BE categoricity. Yeah, so in both directions, so we have computably categorical equivalent structures that are not computably BE categorical and vice versa. Okay, and for the zero jump case, well, what we know for BE categoricity that the relative and non-relative versions coincide there, which is not the case for the classical computable categoricity, as proved by Ketch and Turetsky. And well, here we have implications from BE categoricity to categoricity, but not the other way around. Well, how we achieved all these results, we just directly characterized how those equivalence structures of each kind should look like. Okay, so I will probably not talk too much about it. Yeah, just let me maybe show one of these. The basic case, a computable equivalence structure is computably BE categorical if it has finitely many infinite classes and is bounded. So there is a bound on the size of finite equivalence classes. So, and this characterization is different from the characterization of computable categoricity up to isomorphism. So in particular, from here, we get a corollary that those two notions do not coincide. So we have examples that separate those two notions in both directions. Okay, and we can do the same for higher levels for zero jump and zero double jump. Okay, and this is actually not that hard to do, you know, for the case of bi-embeddable categoricity. So I would say that it is easier to work with bi-embeddability. Well, it was easier to work with bi-embeddability at least for equivalent structures. And then we can also define degrees of bi-embeddable categoricity also in the usual way. So this is the least degree, if it exists, that can compute embeddings between any computable bi-embeddable copies. Yeah, so it's analogous definition to what we defined for computable categoricity with Kalimulian and Rasan-Miller. And well, for equivalent structures, using our characterization, we can immediately say that the possible degrees of bi-embeddable categoricity are 0, 0 jump, or 0 double jump. So an analogous result for computable categoricity for equivalent structures is much harder, much harder to prove than for bi-embeddability. Okay, so what do we know for other classes? We also have some results for strongly locally finite graphs. And this is also an interesting difference. We know that every computable strongly locally finite graph has to be 0 double jump categorical relative to isomorphism. But for bi-embeddability, we have an example of such a graph that is not even hyperarithmetically B categorical. For linear orders, we know that they, and Boolean algebras, we know that they are computably B categorical if and only if they are finite. In particular, we know that there are computably categorical linear orders and Boolean algebras that are not computably B categorical. And then Bajenov, Rosega, and Zubkov looked at higher levels of B categoricity for these classes of structures. And in particular, they showed that we have like a hierarchy of this B categoricity linear orders of finite Hausdorff rank n are relatively delta 0 to n plus 2, B categorical, but not relatively delta 0 to n plus 1, B categorical. And for Boolean algebras, they showed that a Boolean algebra either has a degree of categoricity 0 alpha for some computable alpha, like for B categoricity, or it is not hyperarithmetically B categorical and has no degree of B categoricity. Okay. So this is what we know about B categoricity. And well, the questions here are, what are at all possible degrees of B categoricity? Can we have something, well, more interesting than what we got? And may we have degrees of B categoricity that are not degrees of categoricity for isomorphism and vice versa? Okay, so there are some results in also some relatively new results in this direction. Well, first of all, Bashenov got more examples of degrees of bi-embeddable categoricity. And then Chima and Rosegar proved that if we have a degree D above 0 double jump, then it is a strong degree of B categoricity, if and only if it's a strong degree of categoricity. So actually, if we want to solve this last question, well, then we have not so many maybe possibilities to look at if we talk about strong degrees of categoricity. So maybe we need to look at those that are not strong, or look for them in not above 0 double jump. Yeah, but in either case, even if those notions coincide, that would also be not a bad thing that happens, because well, then we have a hope maybe to have a new tool how to work with this degrees of categoricity. Okay, how to get maybe new examples through degrees of B categoricity. Okay, so it might be also well, depends on how you look at it. So it might be also a nice thing. Okay, good. So that's it about this third group of questions. And now the last one. And well, so we have a class of structures. Yeah, remember we have a class of structures, countable structures closed under isomorphism. And from somewhere we are seeing larger and larger pieces of one of the structures from the class. And we want to say, after seeing finitely much of the structure, we want to say which of those structures from the class we are observing. And in this situation, when we talk about bi-embeddability, we do not have to identify the structure exactly up to isomorphism, but we will be satisfied if we identify it up to bi-embeddability. Okay. So we want just some approximate answer to what we are observing. This is the intuition, and here are some definitions that we would need to answer this question. So these are the definitions that come from algorithmic learning theory. So yeah, we have a class of structures closed under isomorphism, and we assume that we have some enumeration of the structure from the class. Yeah, so yes, effective enumeration, but well, we will also think about some Friedberg way of enumerating them of some complexity, and we just forget about the complexity of this enumeration. And then we say, well, then a learner is a total function. Okay, a total function that takes as input finite substructures of a given structure. I don't know what this should have been, probably C from the class K. Yeah, and it outputs conjectures. Okay. the inputs are finite substructures, and the outputs are conjectures which structure from in these conjectures, meaning indices of the structures from above. Okay, and we do it all up to an equivalence relation. In our case, it will be bi-embeddability, but let's give a definition for a general whatever equivalence relation. Then we say that a learner learns a structure if it converges to a correct index for any isomorphic copy of S. Yeah, so this here, this should be the same S. Okay, so this is S and this is S. And so from some point on, we should, for any isomorphic copy, from some point on, we should converge and start outputting one and the same index. And this index should correspond to a bi-embeddable, in our case, structure to what we are receiving as input. Okay. And this notation for inf and x, it comes from the learning theory. Inf meaning learning from informant, that we receive both the positive and the negative information about the structure, about those finite pieces of the structure. And X is explanatory learning, that this convergence behavior, that's from some point on, we output one and the same index all the time. Okay, and we call a family of structures learnable in this case, if we have a learner for this class. Okay, so, and then we, together with Timo Kötzing and Lucas Mauro, we looked at so learnable equivalence structures up to bi-embeddability and up to isomorphism. And this is the picture that we got, and also effective versions of those two relations. So these are equivalence structures that are learnable up to computable isomorphism. These are equivalence structures that are learnable with respect to computable bi-embeddability, with respect to arbitrary isomorphism, and with respect to arbitrary bi-embeddability. And these implications, they are natural, they are obvious if you just look at the definitions. And what we showed that they are actually proper inclusions. Yeah? So there exists. So we can find an example that is learnable when we look at arbitrary isomorphism, but not when we restrict our attention to computable isomorphism and so on. Okay, and here we actually use those examples, those results about computable BE categoricity for equivalence structures that I mentioned a couple of slides ago. Okay, to distinguish between these classes. Okay, so it would be nice to study the learnability for other classes also, not just for equivalence structures, and do the same for other sources of information. So learning not from both the positive and negative information, but only from the positive information, and for other convergence behavior. Yeah, and it would also be nice to have a syntactic descriptions of learnability up to bi-embeddability, because we have some examples for learnability up to isomorphism. So it would be nice to have something here also for bi-embeddability. Okay, so these are all my open questions about bi-embeddability that I have. Thank you very much.
If you can go a few slides back.
Yeah.
So your result where you were looking at degrees of bi-embeddability for bi-embeddability for strongly, yeah, that one.
This one.
So what is you said not, okay, not pragmatically bi-embeddable. And what's the up and down there? Is it just that or?
So let's see. We code. So it's basically going like this result of Bajenov. So this is coding this kind of pi01 function singletons into. Let's see. So no. So what exactly do we code there? So we are coding some kind of path into this locally finite graph that make it then non-hyperarithmetically bi-embeddably categorical.
Now you have to repeat the question. Yeah, so I was asking for the second theorem, how do you get this non-hyperarithmetical result? Like, yeah, what gets coded here? So that's
yeah. Yeah, so we are yes, that was quite a while ago, but the idea is that we were coding some kind of let's see, we were coding some kind of path into this strongly locally finite graph, and yeah, in such a way that it was too complicated to get those embedded. Yeah, but what's the upper bound? Yeah, I don't know.
Okay.